Very good. So hello everyone. Welcome to the second lecture of our course on Introduction to Quantum Computing, and the actual lecture, if you don't consider the previous one, which was the introduction presentation. So since at least some of you have never worked in Python, Jupyter Notebook, and so on, so I decided to make this intro lecture to the Python and Jupyter Notebook. So my plan for today is to start like from scratch, basically explain how we launch Jupyter Notebook, how we launch it from the particular folder, and then explain some basic elements of working in Jupyter Notebook and basic syntaxes of Python. So this is my Anaconda prompt, right? You can launch Jupyter Notebook from another prompt from the terminal, like a Windows terminal, right? So first, what I want to do is I want to change my directory. So by default, the Jupyter Notebook opens in the directory by used for installation. Okay, so I want to work from another directory from my working folder. Okay, so I need to change the directory. To do so, I do this the code, right? CD, which indicates the change of the directory. And then I just copy and paste the address from my working folder. So in my case, it is something like this. My basically teaching and the name of our course. And as I enter, yeah, so now I am in this current directory. And now from this directory, I'm launching the Jupyter Notebook. So by the way, I uploaded this file that I'm gonna use today to the Canvas system. So please feel free to download and work with me. Yeah, so Jupyter Notebook. Takes few seconds. Yeah. And it's created in the browser, in your default browser. Do you see my browser now? Let me know.
Yes.
Okay. Yeah, so here in my browser, what I'm opening is the lecture 2. Okay, so introduction to Python. Here in the first place, in the first part, I have written this procedure for starting Jupyter Notebook. Then there is something important about the version. So I used to use so far Jupyter 6 version, but recently there is a new one, Jupyter 7, and they have changed the format quite significantly, and I've got some problems with using Jupyter 7. So this is Jupyter 7 now, and I don't like how it works specifically for the Markdown and so on. So very fortunately, we can change actually the format from Jupyter 7 to the format that we used to. To do so, you just go here, open in, and then you have two options. NB stands for notebook, so notebook classic or Jupyter Lab. Okay, so Jupyter Lab is the online format. If, for example, I run Jupyter Lab, you will see how it works. It is like a web browser online version of the Jupyter Notebook. You can do the same things unless you use uh, some libraries that unfortunately we're gonna use. So I suggest that you uh, do your works in the notebook format. Okay, so as I said, let us run this file in the classic notebook. It opens the new window with the file in the format that we used to. Okay, so this is the classic format. This is the Jupyter 7 format. Notice the difference. Okay, so now I can close this one. So the classic Jupyter notebook format. So first of all, a few words about the cells, right? So the notebook consists of cells. Each cell is kind of pieces of code or information, okay? So by default, when you create a cell, this is what you see when you create a new cell. By default, it is in code format. We use code format when we are coding, okay? If we want to write something like writing formulas, lectures, notes, and so on, we use Markdown. So Markdown for text, this is text. Code is for the code. So you also, so Jupyter Notebook can use different types of kernel. So kernel is the basically programming language that you use for coding. By default, Jupyter Notebooks uses the Python 3 specifically. However, you can install other languages, C++, then you will be able to use Jupyter Notebook for other languages. Okay, so we're gonna use Python. And the type of the kernel also indicated here in the upper right corner. Okay, so to create a new cell below the current one, you can type B, it creates a new cell down. You can create a new cell up, you type A, okay? In order to remove the cell, you do double D, DD, yeah, you remove the cell, DD, DD. Okay. Code versus Markdown. I said we use Markdown to write formulas, text, some commentary, and so on. It's very nice platform. So by the way, if I click F11, I can transit to the full screen mode, which is also nice for, I mean, for lectures, for presentations. Yeah, so you can write formulas. The syntax is here is pretty much the same as the syntaxes in LaTeX or MikTeX, whatever you use for writing papers, formulas, and so on. If you never use this, I mean, this is just the matter of habit, right? Please practice because most likely you will use Mictech or LaTeX to write your thesis, diploma works, and so on. So this is how we create a kind of like a new section. Formulas, inline formulas are placed in the single dollar elements. The offline formulas are placed between double dollar elements like this. So if you Control Enter, you kind of run this code to see the result. This is the result, right? You can write different formulas here. You can, for example, you consider this formula like important. You can box, for example, this formula boxed in figure parentheses. Yeah, this is boxed formula and so on. You can highlight text. We will use 3 types of highlighting using this these elements like this. I don't know how to call this. It's the key bottom by the number 1, so you can easily find it right below escape usually. So using this format, we will indicate the pieces of code mostly. Also, if you use star, you italic text. If you double star, you bold text. You can also do triple star. It will be italic bolded text and so on. Markdown makes Jupyter Notebook very interactive. Okay, so for example, you can insert a video file from YouTube video from YouTube website using this command. Okay, so here is how it works for one of the video files from my YouTube channel. So specifically what we're gonna talk about here today, you can find in this lecture 2. However, that lecture 2 in my previous course was kind of more advanced. Okay, so today we're gonna talk more about elementary things. So this material that we discussed today, you can't find this on the YouTube as yet. Pictures. We can also insert pictures in our code. Let me take a picture, for example, of this picture here. Right. So what I basically do, I just copy and paste the picture. It is inserted in a link like this. Control Enter. Yeah. So this is the picture. So you can copy and paste any picture. In your homework, by the way, you will be asked to write some solutions by hand, so it must be handwritten, and then you have to take the picture of your handwritten solution and insert in a appropriate cell. Okay, so practice with this a little. Okay, so libraries. One of the reasons why Python became so popular today, because thousands of people around the world have written a lot of different kind of libraries. So you don't need to code from scratch. You can use those libraries to do a lot of very interesting things. Some examples I will show you today. The libraries that we will be using in this course mostly are NumPy, where num stands for numerical. This is the library for numerical numerical mathematics. Okay, like linear algebra, solving some differential equations in the numerical way. So whenever you have some formula or you write the code to compute something in numbers, you use NumPy. If you ever worked with MATLAB, NumPy completely replaces MATLAB. However, NumPy is free access, right? So no need to pay for the license and so on. All these libraries are free to use, which is extremely nice. SymPy is another library for symbolic math, for symbolic mathematical operations. We will use this for doing analytical calculations. Okay, so whenever you have a formula in analytical form and you want to work with those formulas and so on, like in an analytical way, you use SymPy. And Qiskit. So this is the third one. I still like using Qiskit, even though there are some other interesting libraries available today. Probably I will use something else for the quantum simulations, but I used to use Qiskit, and Qiskit, by the way, is the library created by this company IBM that provides the access to their quantum computers, real quantum computers. So you can use Qiskit to write quantum codes, to execute those codes either on your machine or to the remote server of IBM, or not only server but also the quantum computer. So NumPy usually comes with the Anaconda distributive. So if you install your Python through Anaconda, most likely you will have NumPy already installed. SymPy, probably not. Qiskit, not for sure. So you need to install them. How we install the libraries? Either directly in the Jupyter Notebook or in the prompt, you simply write pip install and then the name of the library. If you use Anaconda, you can also use conda install and the name of the library. I usually use pip install and the library. So for example, if I don't have SymPy on my computer, I simply run this cell, and in a matter of few seconds, you will get the library installed. In my case, it was already installed, so I'm ready to go. As you install the libraries, you need to tell to your Jupyter Notebook file project to use these libraries and how you name that. Okay, so these two lines here import two libraries, NumPy and SymPy, and I give them a name, NP and SP. So this name, it doesn't really matter. what you use for the name of the library, people usually use NP for NumPy, SP for SciPy, SymPy, and so on. But this name literally up to you, okay? Because what it affects is only the way you work with the library. This is the way you distinguish between the libraries. For example, if you would try, for example, to use sine function, like sine function of 0, you would get the error because Jupyter does not understand this function yet. However, if you use something like np.sine, Jupyter will use this sine function from the NumPy library. And of course, the result is 0. For another angle in radians, you will get something else. You can use the same function, like sinusoidal sine function from another library, from SymPy. You can do this, SymPy, and you notice the difference, right? In NumPy, it gives you the number, but I mean the answer. In SymPy, the result is something like this. However, it of course returns the number if it can. So, for example, for a sine 0, we know the answer is 0, so it returns 0. There are other, of course, mathematical libraries. For example, you can import math. Math is the standard mathematical library that usually comes with the general standard standard Jupyter or Anaconda distributive, so you can use math. Okay, so for example, I can for example use just like this import math without saying anything about this. I mean, how to name this, library. Then I will be able to use, let me show you. Then I will be able to use sine function without any naming, because from my math, it will be, no, so from if I do from math import all, I will be able to use sinusoidal function without the name. Okay, so this is the matter of how you distinguish between the libraries. If different libraries have the same function, how you will use this function from different libraries. If I can go without as np, of course, then I would be required to write the total name of the library, numpy dot sine numpy. Okay, so this as np just to make it tidy and concise. Okay, so let me remove this part. We import numpy, sympy. Okay, libraries. Oh, sorry, libraries. The variables. Variables is basically the data, right? The data that we feed or insert to the program that we use to do in a program. Simply speaking, variables can be, for example, something like this, right? You can say sum A equals to 10, B equals 5, and then you can run this code, and you will see that, so from the output, you see that B gets 5, but A is not returned because usually by default, Jupyter Notebook returns only the last output. Okay, so A is there. For example, you can create another cell and check the value for A. So A is in the memory, but it didn't return in this cell here. To fix that, to see the both results, you can, for example, use function print. So print basically prints the value of the variable. So in this case, this line of the code and the both line of the codes are executed, and the result 10 for A and 5 for B. By the way, do you have any questions? If you got any questions, feel free to interrupt at any point, as usual. For example, right, you can use Jupyter Notebook as a calculator. For example, in your physics course, you might get a problem like this to calculate the acceleration of gravity, right? This notorious G. We know that it's something around 9.8, right? But the formula how we calculate this is this one. So it contains the gravitational constant, G capital, which is 6.67, 10 to the power of minus 11. If you never code, by the way, you can, of course, write something like times 10 to the power of minus 11. The result will be, oops, yeah, this is the habit from Mathematica. You would write something like this. The way we write power instead of hat, right? Like in Mathematica, for example, we use double star. But the more professional way is to write E and then the power. So this is the gravitational constant, the mass of the Earth, radius of the Earth. So the acceleration of gravity is simply this, right? So it depends on the distance, and at the surface of the Earth, the h is equal to 0. So this is the formula for gravitational constant. Oh, sorry, for the for acceleration of gravity. This is the result. So in order to print different replies or all replies, you can always write print A, print B, and so on. Sometimes, I mean, this writing print all the time is pretty annoying. Instead, you can use this from the standard library. You can import the interactive shell function. And this interactive shell function allows you to, makes you able to tell to Jupyter to provide all the outputs, all the results. So by the way, let me restart and clean the output. Okay, so at any point, of course, you can restart your kernel and, for example, clean all the outputs. I just need my libraries. So I import the libraries. And by this line, I'm telling Jupyter that I want to see all the outputs, okay, all the results. For example, here, as variables, I can use integers, just as I did recently, 5 and 10. I can do floating numbers, right? Like pi, 3 times 14, 15. I can use strings, hello quantum world. Okay, and I announced all these variables, and now I want to see all the results. And here are the all four outputs. This is because we enabled all the outputs by this line. However, sometimes, for example, if I iteratively run some calculations, I don't want to see all the outputs, right? I can write the same line, but say last expression, right? Instead of all expressions, I do last expression. In this case, my program will return just the last one, which it was for default. Okay, so let us do all for now. As I said, we can use Jupyter as a calculator. We've got different arithmetic operations, plus, minus, time, the power, ratio, dividing, integer division, and the division with the or remainder division, right? So which returns the remainder from your division. I run it. So for A, how much is 10, B 5, we've got all the outputs. Notice that the remainder, right? 10 divided by 5 gives you 2 with remainder 0. So it returns only the remainder. The variables can be also Boolean. Boolean variables or operators then can be only of two types, true or false. Okay, true and false. How we work with these Boolean operators, we use comparison operations. Okay, so we can ask our program if two entities, two variables equal. We can ask if they are not equal, either one is greater than another one, less than another one, greater and or equal to, or less than or equal to. So for example, if I comment this one, for example, if I want to see the result if 2 is not equal to 11, so that's true, right? 2 not equal to 11. If, for example, 11, that's false, because 11 equals to 11. I can do another one, for example, if 1 greater or equal than 2. Of course, that's false, because 1 is less than 2. If I do less than, then that's true. Quite often we need to change the type of the variable, right? So for example, I insert some number, and Python save this number as an integer or float. floating number. This is floating number. By the way, notice that in Python, you don't need to like always indicate specifically the type of the variable, which is very nice because in other libraries you always have to indicate the type. The Python um, identifies the type by itself, so you no worry about that. You can convert this number, for example, to a string, okay? Because like when you write some response using your keyboard, usually that response is considered as a string, and you can convert your string to the float, or you can convert float to the string. So you just use this, for example, str, and it converts this number to the string. Okay, and then you can, for example, concatenate this number with the words, with the strings. So you can convert type of the variables. So do you have any question about the variables?
No.
This is okay. Yeah, this is pretty straightforward. So next, functions, right? So if you got variables, of course, you want to do something with those variables, and the way you operate with variables, for example, in math, right? You use functions. Functions are operations that put in the correspondence or establish the correspondence between one type of variables and another type of variables. Okay, something like this. So, for example, sinusoidal function, right? It put in the correspondence the angle, the value of angle on the circle to the values from -1 to 1. Okay, so it's like function is the way we establish correspondence between some things. In Python also, function is something that can do some operations. And if you write function, you can use this definition of the function in different parts of your code. So like if your function is not just sinusoidal or some typical mathematical function, but something else, and this function can be quite sophisticated with a lot of lines of code, so you don't need to write this part of the code every time you need this function. You can give this function a name and then call this function whenever you need it. Okay, so in Python, the way you define the function through operation def, and then function name, and then parameters, then column, and what this function is supposed to do, and what this function is supposed to return. Okay, so for example, if I create a cosine, right, I do definition, the name of my function. I can use whatever name. It can be cosine, for example, cosine. So this is my function, and what this function does, it returns the number of cosine that I take from NumPy library. Okay, so this is the function. This way, my cosine function, if I do, for example, 0, I know it will return me 1, right? I can use SymPy. the same way here. So it will be strict 1. Yeah, so this is the way how we define functions. Of course, as I said, the function can be not just mathematical, it can be any type of operation that you want. For example, I've written something like this. So it's a greeting function. Like it returns hello, and then whatever you insert as a name to the variable of this function. So for example, if I greet Alex, it will return hello Alex. Hello world, it will return hello world. Notice that we write this name in the string format, right? Because the output must be string. This is also the way how we do this operation of concatenation. Okay, so concatenation, this sophisticated name, is just combination. Okay, so concatenation is the way to combine different variables. Usually we use that when we need to combine to create some kind of string response, like here. So here I put this line. I guess I need to transit back to the last expression output. Let me see. So if I run this, I will get error, right? Because NumPy, oh sorry, Jupyter doesn't understand this sign. It doesn't understand what does it mean, because we haven't indicated which library we want to use. Okay, and also pi. So pi also not defaulted. I mean, it returns pi here because we announced it later in this line here. Okay, it's because, so if I do something like this, it will forget my pi. So it's still in the memory. Okay. Anyway, so it's not the pi that's from the library. This is the pi we created and set to the memory. For example, if I do pi equals 1, now it will return me pi 1, right? So it is just the name of variable. What I'm trying to say is that every time you use mathematical functions, you need to tell Python which library you use. NumPy here, for example. Let me comment this. So in order to comment, by the way, you can use control right slash and run it. Okay, yeah, it works, but it works badly because the pi is wrong, right? So now this pi is just a variable we recently created. In order to make it like correct, I do, for example, NumPy pi number. Okay, so this is strictly, I mean, the correct response, correct answer. Similarly here, cosine, it doesn't understand. I need to use something like NumPy cosine or SciPy cosine, and then either NumPy or SumPy here. It returns something like this. SumPy. Yeah. Sometimes we will be using this library called VPython. VPython is a library. It's a quite extensive library that we use to teach physics, okay? Because this V here stands for visualization. So you can use VPython library to visualize physics instead of writing boring formulas for how mass moves in a gravitational field and so on. You can do the animation of this. And the way you do this, you use VPython library. Again, if you want to use this one, if you want to practice with it, you can also install it. It's a lot of fun. For me, I want to use this VPython because it provides easier syntaxes for vectors. Okay, so for now I'm gonna use this VPython just for vectors. And also, if I do from library import star, this star means I import everything for this library. If I do so, I don't need to use the naming for the inbuilt functions. Okay, so if I import everything from VPython, which contains sinusoidal function and the pi number, I can use this function and the number without giving its name, without writing something here. Right, so the answer must be 1. Okay, so now this sign function is used from VPython. Similarly, I could do from NumPy, import everything, and then I would be able to use functions without giving this name and p here. However, this way I wouldn't be able to distinguish between libraries. Okay, so let me come back to here. This is the reply. So this way I'm using inbuilt sinusoidal function and cosine function from VPython. This is for what? I don't know. Yeah, and of course, not only sine, cosine. There are many inbuilt functions like square root, right? This is the square root function. For the logarithmic, you could write something log logarithmic. Logarithmic 1 is 0, right? Logarithmic 0 is not defined, so it is mathematical error. And so on. Yeah, so a lot of inbuilt functions. Do you have any questions about this part, about functions, their definition, and inbuilt functions use?
Is there a website we can find more functions? Just that
Yes,
you know
I
about?
mean, that depends on the library. For example, if you go to NumPy website, right? NumPy website, you can find documentation. It looks like this. So NumPy, this library gets its own website. And here, getting a user guide, I guess. Yeah, and all the formulas, functions, everything is here. You can use the search.
Awesome, thank you.
Yeah, this is NumPy. I particularly like SymPy SymPy library. It provides a lot of documentation in terms of I mean, from different areas of physics. For example, you can use you can, for example, do quantum here. You can search for quantum, and it provides a lot of inbuilt functions, you see, that you can use for quantum computations. If you ever, for example, heard about quantum Fourier transform, QFT, quantum Fourier transform, it's here. So you just need to upload this function to your Jupyter Notebook file project. That's it. So you can use the any prepared inbuilt function from these libraries. SymPy gets a lot of quantum libraries. Not only quantum, there are much more, like classical mechanics. So basically, whatever you learn in classical mechanics, you can find here. Matrices, Pauli algebra, somewhere, yeah, here, Pauli algebra, Pauli matrices. We will use them for computing. Also here, a lot of things, and not only SymPy. There are many others. For example, Qiskit, this IBM library, it also has inbuilt functions for computation, for Pauli matrices, and so on. So you don't need to write everything from scratch. It's already done for you, which simplifies a lot. Whatever you do, you don't need to start from the beginning. All right, so of course, the purpose of any computational language is to work with a lot of variables, right? A lot of data. And you need to somehow arrange this data in this or that way in order to be able to call for a specific element in that data in the data. Okay, so the way we arrange data in Python, pretty much similar to any other language, is arrays, lists, vectors, matrices, and so on. So the difference between matrices, vectors, pretty much simple, right? We will discuss what are vectors, matrices, in what is coming, lists and arrays. I think this is the two things that people probably don't distinguish. So list is just a combination of elements, and their type can be different. It can be integer, it can be strings, it can be floating, and so on. And list doesn't care. So you can combine different variables, elements of different type, of different nature in a list. A list can be also a list can also contain lists, right? So for example, something like this is also a list that contains lists. Okay, it can be a list of lists and so on. So list is just the way you number some elements. Vectors are more specific for numbers. Okay, so a vector, for example, this is my vector A. I use vector operation without any name here because I use VPython. Okay, so there are another way to work with vectors. I will talk about this in a few minutes. But in VPython is just very tidy or very easy to understand what's going on here. So here I create a vector A. So I give it name A, and these are the components of my vector. So it's X component, Y component, Z component. Okay, so when I can print this vector, this is the result. I cannot use something like quantum, for example, here. Right, so vector is for numbers. It can be floating, doesn't matter. But integer or floating, not strings, not something else. Numbers. Vector operations. I can do vector algebra in Python. So for example, if I create two vectors A and B like this, I can of course sum vectors. Sum of two vectors is just the sum of each component, x plus x, y plus y, b plus b, right? I can do dot product. So if you don't remember, please refresh your mind about dot product and cross product. Dot product, you take two vectors, you do the dot product, and the result is a scalar, right? The scalar. This dot product is the projection of one vector on another vector. By the way, for vectors, you cannot write something like A star B. It doesn't understand this star. What is multiplication of two vectors? For constant, that's completely simple. But for vectors, since product of two vectors can be either dot or cross, so you need to specify which product you use. So you cannot do product just star. You need to use either dot for the scalar product of two vectors or cross. The result of the cross product of two vectors is another vector, right? This vector is equal to the is equal to the area of the parallelogram made by these two vectors and points in the direction which is orthogonal to this parallelogram surface. Okay, so I mean we will talk about this, maybe not about cross product. Cross product is less important for us. It's just another way we compute the product between two vectors. So let's say, for example, if my vector A is something that oriented along x direction, my vector B is a vector oriented along y direction. By definition, this cross will be directed along z direction. So I expect this and these elements to be 0, and this guy will be equal to something. Great. STEM. Vector components. Yeah, if you use VPython, you can operate with the components like separately. For example, for vector A, my component x, ax is 2. So here I can ask Python to return my ax component, which will be 2. For by is going to be 5. Okay, so this is the result. So I can work with components separately. So when I need that, for example, if I write square root of the sum of the components squared, right? It is the magnitude of the vector, basically the length of the arrow that represents the vector. So I can do something like this, and it returns me the length of the vector. Of course, magnitude function is inbuilt function. I can use inbuilt function magnitude like this. So the result is exactly the same. So indeed, it returns the magnitude. If I divide any vector by its magnitude, I've got the vector with unit length, with unit magnitude. This operation is called normalization of a vector. So it's a vector that represents direction in space rather than any value. Right, so this is the normalized vector A. This is vector A. I do normalization of this vector. Indeed, how it works, I take this vector and divide each component by the magnitude of the vector. So if I remove this, I will see completely the same response. So my point is that of course, you have to understand how this or that function works, but after you do understand, you can simply use like inbuilt functions without writing them so detailed. However, in our course, just like usual, for vectors, for lists, for arrays, we will use NumPy. Okay, because NumPy, the purpose of NumPy is just like this: the work with arrays of elements. So here I use NumPy function array from NumPy library, right? And the way I create I create array is like this. So and NumPy array, and then in parentheses I write the array. Array is in the rectangular brackets and divided by comma. Okay, this way I create the array H. H here stands for horizontal, I guess. So if I print the result, this is the horizontal array. Again, if I change this to some number values, yeah, you see it doesn't work properly because it changed all the elements to the string. So again, array is mostly for the numbers. This way I create horizontal array. I can do a vertical array. Vertical array created by the same way, but you indicate that each element is the new row, right? So if I return this, yeah, it is a vertical array where each element is the first element in the corresponding row. Instead of using this complicated way to create an array, the vertical array, I can simply write horizontal array and then use this function reshape. Okay, so I take this array, which is horizontal one, and then write dot reshape, with standard -1, 1. So we don't change this. It's just the way how we indicate how we reshape this how we reshape this array. So if I do that, I will indeed get my vertical array, which was reshaped from horizontal one. There are some inbuilt ways to create some simple arrays. For example, zeros, right? This is the array of zeros. This is the array of ones. This is the response. For example, if you need to create a not empty, but the array of consisting of many zeros, like 10 zeros. Yeah, so it's created automatically. It can be a zero vector, for example. Do you have any questions about arrays, vectors? Well, I haven't discussed matrices because we're going to discuss matrices basically next time. Do you have any questions regarding this part? I've got a comment, a new message.
I have a question.
Uh-huh.
Can we do like a file handling, like get data from a file? Is that possible or?
What do you mean? You mean saving this?
No, like can we load data from a file and put in a program where you're gonna send the data to a file or take data from a file?
Oh yeah, of course. The import and export. I didn't put it here. I mean, it can be easily found. Yes, just one line of code, but be kind of. So what is important is that you need to, in order to be able to use data from a specific folder directory, you need first to change the directory. This is the way, I mean, I showed you how to do so in the beginning, right? This cd command and so on. After you do that, yeah, then you can simply upload and export data to that directory. I have an example that I want to discuss later today as like a final example of the use of Python. So we will touch this point one more time later today. Yeah, so of course you can import, export any data for sure. Yeah, and the comment, it's great. Help, thank you. Yes, thank you very much. Loops and conditions. Okay, so you got variables. You can structureize variables in form of arrays, vectors, lists. You have functions that help you to work with data, with numbers and so on. Now, the most important thing, I guess, is to how to create this the protocol, right? The procedure, how we work with data. Okay, this is to do so we use loops and conditionals. Conditionals are some logical elements that we use to work with data, and loops simplifies the work, right? I mean, it's better to look at the theory and a few examples. So one loop typically used in Python is loop for. Here is the syntaxes, pretty simple. So for some variables, some variables, in some array sequence, then you do column and enter, and Python will transit to this point here, not to the not will align these lines, but it will get some tab, right? This space. So this space indicates that whatever is here, it will be executed as a part of the for loop. For example, and also example of the use of this function range. So for loop, what it says, for element I, this element I can be, again, whatever, it can be t, in range from 0 to 5, okay, print t. Okay, so the result will be all elements in the range from 0 to 4, because Python numbers counts the things not from 1 and so on, but from 0. So the first element is 0. This is better to remember, to keep in mind. You can change this. You can start from 1 up to 5. Okay, so now it counts everything from 1 to 5. You can also do the step. Instead of step 1 by default, you can do 3, something like this, and so on. Yeah, so what it loops does, it changes t according to this list, and simply prints this this t for every step. Notice this space, as I said, because you need this tab space to indicate that this print works as a part of this for loop. For example, if you do this, it wouldn't work. It doesn't understand. It can print t, but it doesn't understand which t to take. So basically for t in range and to do what? You can do something, I mean, you can simply put constant, I guess. And then it will print the last element in the in the range. So must be tab space. So next one, like conditionals, conditional, pretty important one. It's called if, elif, else. If, elif, else. So it's a logical operation, conditional, and this is the syntaxes. Very straightforward. It's basically the way how you think, how you logically think about something. If it is raining today, then if it is raining today, then I take umbrella outside, right? Else, meaning no rain, it's a sunny day, I take whatever, a jacket. Indeed, it is very natural way about thinking about things. So it's a logical way to do some computation. For example, if 0 is greater than 0, then print this line. Else, meaning that if it's not true, right, then else print this part. You can run this and you will see that this is false, right? So it will print this line here, non-positive. However, if I put 1, indeed 1 is greater than 0, it will print positive. More realistic example. This is our grading scale, right? So you can write a simple code that will predict the grade that you will get after the course. This is the grading scale. You starting from the top. and do like line by line. So for example, you have a score, right? You don't know the score. This is your score. If your score is greater than 90, which means you will get A or A minus, right? So you print A. So, however, if your score is less than 90, this part of the code won't be executed, and it will proceed to the next one, a leaf, right? So if it's greater than 80, 80 is for B grade. If your grade is less than 80, it will proceed to the next one, and final one. So if your score is, let's say, 100, of course you will get A. However, if your score is 90, you will get, if it's 80, you will get B. 50, you will get D, I guess, F, you will get F, and so on. So indeed, it is kind of very nice way to create some logic, to insert some logic to your program. Do you have any questions?
No, sir.
All right. While so while conditional, it's simply this is the same like to say until, right? While this condition is satisfied, then do this code. Like until it is raining, I am sitting home. Or while my count is less than 5, return this. Return this, and then you of course can change this. You can do count plus minus, oh sorry, plus equal 1. So this plus equal 1, you know, it is for adding 1. So by this you simply increase the number. So for example, starting from 0, while this count is less than 1 or is less than 5, do this part of the code. The code prints the current count and then increases the count by unit. And after it's done, the rest of the code will be continued. So this line here will be will be calculated too. So what it will return? It will return a list of elements from 0 up to 5, not included. And then the last one will be a loop ended when count reaches 5. Right, so pretty straightforward. So you can do computation using these loops and conditionals. And you can arrange these computations in functions and so on. Now let's talk about how you represent the data, right? You represent the results of your computation. To do so, like traditionally, we use this matplotlib library. Most likely you will need to install it. Please do. In my case, it's already installed. So it's already there. In order to use function plot, pyplot from this matplotlib. Matplotlib is a library for creating the very nice scientific pictures. I bet you will use this matplotlib a lot, especially if you will write some papers, articles to be published, and so on. So matplotlib must know. in order to use it, I import this function and give it a name PLT. Right. How it works. So let's assume I have some array. I create array of elements from 0 to 10 with step 1. So this is the result, right? Array of elements. I can plot some function. So now I want to use this x as a variable to some function. Okay. This function can be, for example, just x squared. So in order to plot this function, I do plot equal, so just any name, it can be whatever name, equal to plt, which is the name of the function, dot plot. Plot is a function that creates the plot itself. And then first always comes variable, and then the function, right? So this is the result. You can do other things like, for example, what sinusoidal function of x, sinusoidal, because I need to indicate from which library I use sinusoidal function. I'm gonna use from NumPy. This is my sinusoidal. Not good, right? Because I need to add more elements to my array. It's already better, and so on. So this is the simplest way to plot something. If you have some, if you have a function, you have the variable, you can quickly plot the result of this function. It can be cosine, of course, and so on. Let us consider a physical example. So in the basic physics, you used to compute something like this, right? It's a uniformly accelerated motion, the coordinates of a body with a given initial velocity v0 and moving at the constant acceleration a, right, as a function of t. So it's basically the trajectory in one-dimensional trajectory of a movement of some object in a with a constant acceleration. This acceleration can be the gravitational field. Then again, it will be the movement in the gravitational field. So how we can use this formula? I heard some noise. Do you have any, Joseph?
Say again?
Do you have any question?
Oh, no, I'm sorry. I accidentally unmuted.
Okay, yeah, no problem. Please.
I'll try and mute back.
Okay. Yeah, so let's say we have this formula, right? How we can how can work this formula? So first of all, you need the initial conditions, the coordinate in the initial moment. I denoted by 0. I'm giving the 0. Velocity, initial velocity is going to be 1. Acceleration, which is this parameter in this formula, and the discretization of time, dt. For now, it's 0.5 seconds. If I want to indicate that it's second, I do this commentary and then second, for example, right? This is my this is my this is the initial coordinate. This is initial velocity. Acceleration. Then what I'm what I say here is that while or until time is less than 10 seconds, so I'm changing t, and until my t reaches 10 seconds, this program is executed. So I take the t, then increase this t by the discretization time dt. For this new time, I substituted to this formula, which is this one, right? Our original formula, and and compute the result. Then it increases t by a factor of dt, the next one. Substitute here, computes the coordinate, and runs like a loop. Okay, so for every time, for every step dt, it obtains the coordinate x, and the result will be the array of coordinates. Why I don't see anything here? Because I need to create t, right? So my starting t must be 0, right? Yeah. So this is the coordinate. We see that we have the initial velocity positive, acceleration is positive, so the body just accelerates. The coordinate is always positive. Of course, if I do negative acceleration, it will move first in the positive x and then slow down and then move to the negative x. Right, so positive, negative. Let us do 0.5 for acceleration. Yeah, so this is the body started from this coordinate, moves, and then let me see. Yeah, so it's let me actually decrease this. Let's do 1. That's not good. Let's do, for example, 3. I'm trying to demonstrate what? I'm trying to say that initially coordinate increases and then started decreasing. Since this point, it's decreasing and goes back. So here the particle moves to the positive x, slows down, and this is the point of return, right? So the particle starting moving to the negative x, and so on. Yeah. So of course, I can increase the discretization. I can just make it, for example, 0.1, and I've got much more discretized response. So let us jump back. Of course, I want to, yeah, T0. Of course, I want to plot this result, right? In order to plot the result as a function using this PLT plot function from the matplotlib, I need the array of time and array for the coordinate. Okay. The way we create arrays of coordinates using function, for example, while I create first the empty list of time, empty list of position. And then while this part of the code works, it computes the new time and new coordinate and append to this initially empty list. So at every cycle, it appends, means adds the new computed value to the list. Okay, so it starts from T0, it records this value to the empty list for time, then computes the coordinates, then adds discretization to the time to get the new time instant. Then for the new time instant, computes the coordinate, append this new value to the list, and so on. So in result, you get two lists of data, time and position. Okay, similarly, we already have this matplotlib inserted. You can do PLT plot, time and position. And this is just the style for the graph. Right, so if I do this is the acceleration, I can do, for example, the start for the starting point. I can do something like this. So yeah, it changed the coordinate. I can, of course, make this graph more fancy. I can add the name of the X label, which is time. Here I can add the Y label, which is position, like this. I can add the name of the graph as a title, right? So it's pretty much straightforward. I can do grid. If I do true grid, it will add me some grid to this plot, so it's even more nicer. And so why I don't? Yeah, usually we also do PLT show, because usually it also generates some extra numbers here. In order to get rid of them, we use plt.show, but probably in this case it's not required. Yeah, so this is the trajectory of our particle. So let's say my particle moves in the gravity field with x coordinate is the amplitude, the attitude, the height. The gravitational field is minus 10. This is the acceleration of the gravity, right? I'm starting from let's say 2 meters, and I'm jumping from or 1 meter, and I'm jumping from the table with velocity, I don't know, maybe 0.5 initial velocity of my of me jumping from the table, whatever. Yeah, if I compute this, I've got the my trajectory, right, as a function of time. As a function of time. Yeah, I mean, of course, up to the dimensions, because this is meter per second. This is meter, but yeah, of course, this must be larger, and so on. So the point is that, yeah, you can compute things, you can represent things, and so on. Of course, we can use different conditionals and loops, like simultaneously. One example of this, I will try to recall some simple way to find prime numbers. Okay, so you remember what is prime number? Prime number is a number that can be divided by 1 or the number itself, right? So let's say 5, so let's say 10. 10 can be divided by 10, by 1, by 5, by 2, so it's not prime. But 7, for example, or 3, it can be divided only by 3 or 1 and nothing else. So it is a prime number. So because of the importance of prime numbers for some areas of quantum computing, specifically for Shor's algorithm, let us write a simple code to find all prime numbers of some of some specific number. So let's do number, and let's make it 10 for just for now. So what I do for this number, I need to for basically I need to take all the numbers from 2 up to 10 and check that for every number, for all of these numbers, the so what I'm trying to do, I'm trying to find all prime numbers from 1 to 10. Okay, so what I need to do, I need to take every number between 1 and 10 and check that it doesn't divide with the remainder. That does not divide by any number with the remainder. In that case, it will be the prime number. So so let's search for all prime numbers from 1 to 10. So what I do for some I, right, in range from let me see, from 2 to number. Let us check what it does. Print I. Yeah, so it prints from 2. I'm not interested in 1 because any number is can be divided by 1 without a reminder. I don't like number, I need number plus 1. So it's up to 10. Okay. So for every number, I need to check that for all j in range from 2 up to this specific I that is taken at the previous stage, right? That I divided by, not divided, but divided with the remainder. What's the remainder of dividing I by j? And if it's not, if it's equal to 0, if it's equal to 0, if it's equal to for I in range, for j in range, if if I divided by j equals to 0, then meaning without the remainder, right? Then I break this this computation, right? Otherwise, or else I print the number I should be something like this. 2, 3, 5, 7. Yeah, looks good. let's do maybe 100. So if I do 100, this code searches for all prime numbers between 2 and 100. Okay, so yeah, you can see any number in this array is a prime number. Very good. Yeah. Okay. Let me remove this one. Yeah, final example as I promised. Okay, so in Python, there are many different libraries. I mean, many, it means really a lot. You can you can subscribe, for example, for Twitter, for Python Twitter. Quite often they publish some new libraries or some interesting libraries. Some libraries can remove fonts from pictures. Some libraries can do, I mean, a lot of things. It's like you can name it. One library that might be interesting for those of you who are interested in research can be something like this. So PIL library is a library that allows to work with images and particularly do some operations like Fourier transform of a picture. And by this code, I'm going to show you why this can be interesting for research, for example. Okay, so here I'm opening a picture that I saved to my working directory. Okay, so I don't need to change directory here and so on. So it's very simple. This is exactly the way you import some, for example, picture. Okay, so here I'm importing a picture called some structure one. Okay, and then I do fast Fourier transform of this picture. And let me show you the result and why I do so. So this is the picture I downloaded from the internet. It's a electron microscopy image of some very simple like nanoparticles on a substrate. Okay, so you can fabricate something like this from silicon, for example, or gold using e-beam lithography. We can fabricate a structure like this at our nanofabrication facility. And one thing you notice here is what? The picture itself is pretty periodic, right? So it gets some periodicity. And the fact, like, one thing why you want to make a Fourier transform, right? When you do Fourier transform, you change the basis, right? It's like if you ever heard about Fourier transform for time analysis. Let's say you have a signal in time domain. I'm talking now to the microphone. The microphone converts this signal to the analog signal, like time variation of the current in the wires. But we never worked with this time domain signal. What it does next, it converts the signal from time domain to the frequency domain with a number of frequencies, right? So we convert time to frequency domain. This is nice because in frequency domain, the signal can be represented just like a table of data of discrete frequencies and their amplitudes. So you can save, for example, music, right? Something like this you do when you save some file in the MP3 format. You have analog signal, you convert that signal to the, let's say, frequency domain, it's just not just frequency domain, but it's in another domain, and you save your music file just like a table of data. Okay, you can do the same with images. And when you do Fourier transform, FFT stands for fast Fourier transform. So it's another way to do the Fourier transform analysis. So you do the fast Fourier transform of this picture, and you notice this discrete grid, right? So it's kind of grid of small points. And this grid is also periodic. So the fact that this Fourier transformed picture also periodic, and each point, each digit here stands for the mode, or for how to say. So the more points, these periodic points in the Fourier transform picture, the more periodic the picture itself. Okay, so this Fourier transform analysis of this picture tells me that the structure is very periodic, okay, with a very good periodicity. Okay, in contrast, I also find another structure. I gave it a name str2. This structure is, I would say, amorphous. So it also consists of some granules, some particles. It also electron microscopy image. But the Fourier transform analysis shows no orders, this no points, no periodicity, right? So Fourier transform shows that the picture is not periodic, something like that. So you can use these functions to do some very useful things. Yeah, so this is pretty much it. Let me stop my recording and then we can quickly discuss.